Hi guys, today in store is around 685, and well yeah, it's just the div 2, should be fun. I'm going to do the traditional things. First I'll update the sub count as always. Yeah, and that's it. Also, if you haven't heard, there's a new topic stream coming up. You can go to my channel and essentially vote using this community tab, and then there's like a poll here, and you can pick a topic. That's generally how it works, although it may have been like hard to see before. Yeah, so that's the future. There's even more stuff in the future. I will do that as it comes along. For now, we can just do this problem. Divide n by one of its proper divisors, or subtract 1 from n if n is greater than 1. Okay, is there ever a good reason to not do 2? That's the question. Is there ever a reason to not do 2? Like, let's say we have some number like x, and x is divisible by 3. Or say, for example, 105, then we get 35. But if we go down 1, then we get 104, and then we get... Oh wait, actually we do want to divide by like the biggest thing possible, I suppose. Wait, what am I saying? If something's even, we can divide by the thing that isn't 2, and then make it 2. And then we'll do it in that many operations. Yeah, I think that's always optimal. It'll take at most 3 moves to if it's an odd number, make it even. So, for example, 104. And then we divide it by the thing that isn't 2. We divide n by n over 2, and then therefore we get 2. And then we go down to 1. That's at most 3 moves. And I think that will work, because any other number that we get in this step will be at least 3, which means that it will also take at least 3 moves, because we have to do at least 2 decreases to get to 1. And we have to do 1 thing to divide. So, that should work, except for when we have 3 itself, and then that's simple, it's just an edge case. So, that should be it. Yeah. Even if it's not like the only optimal solution, it is an optimal solution to only divide by n over 2. N mod 2 is equal to 1 minus n. If n is greater than 1, wait, can n be 1 itself? If n is greater than 1, and divide by n equals 2, plus ants. If n is equal to 2, plus ants. What? So 1, 2. Actually, I can just ignore this. Make it if n is greater than 2, set it equal to 2. Then that way I won't waste another operation. Okay, seems like it works for small numbers. Let's test 5 as well. 1, 5. Should be 4, 2, 1. Yeah. So essentially, decrease if it's odd and it's not 2 itself. Then if it's greater than 2, make it 2, and then if it's 2, we have to decrease again. Alright. This name that I don't know how to pronounce has Q queries on a binary string S. Okay. Is to determine whether there exists a good subsequence that is equal to the substring SLR to RI. Substring is a string formed by characters. Yeah. String A is said to be a subsequence if, yeah. And it's good if it's not contiguous. Huh. Well, I suppose consider some string S, like for example 1 0 0 1 0 0 1 0 1 1 1. I don't know. And then we ask for some query like this. Now we just want it to be non-contiguous, which means we can kind of just move any of these characters to the end. And then, yeah. So like if we can get rid of this 1 and put this 1 somewhere else, then we're done, because it's like automatically non-contiguous. And say we couldn't. For example, say like there's nothing on this end, and the only way to finish a query is to do something on this end. If we can't move this, if we can't get rid of this character in this string and move it somewhere else, then like there's no way we could ever have this character at the beginning, because to not be able to move this character means that all of this has to be zeros, which means that there's no way to have this 1 outside of this substring. And the same goes for the end. So essentially, either we can move this, or we can't have it at... Either we can move this, or it's forced to be inside the string. And if this is forced to be inside this substring, then everything else is too, because it's to the right of it. So essentially it boils down to checking, can we move this somewhere else? So do we have a 1 in this prefix, or do we have a 1 in this prefix? And if this, or in that suffix. And if this is a 0, then it's simply checking for zeros. I believe that is it. We can do this naively because the things are tiny, even though we can do prefix sums, but it's not that important. N, Q, and then S. L exclusive. If Si is equal to SL, pos equals 1. That was a bit loud. Okay, right. Then we have this. Okay, so essentially, to do this, we check here if we have a 1 in this prefix, that is, if we have any character that's equal to this one, and here we check the same thing. 2, 4, all this makes sense. Yep, 1, 3, yep. Go exclusive to L and exclude R. Seems legit. Yeah, okay. String equality. You have two strings A and B, each of length n, and an integer k. We only have lowercase English letters. Wants to convert string A into string B by performing some, possibly 0 operations on A. One move, you can either swap AI and AI plus 1 for some index, or if they're all equal to 1 character, replace each one with the next character. Okay, so we can move the string however we want. So we can move the characters of the string however we want, because we can swap and we can sort an array using swaps. Think like bubble sort. So we can sort an array, we can get any ordering, which means that essentially we don't care about the ordering of the characters. What we care about are the numbers. So we keep track of the counts of each character. Then once we do that, because like this contiguous thing doesn't matter, because we can move the characters however we want, so if we have enough, we can make them contiguous. So we just need to make the number of characters equal. And essentially, I think that's just greedy, basically. Like, we have to have enough, and at the same time, we have to not have too many. So let's see. What is this? What's the input? So C into N into K. It's just counting characters. And then, okay, for I equals 0, I is less than 25, I equals plus 25, because we can't, like, have the same amount. Okay, so first of all, if we have less characters in S, we're going from A to Z, or A to Y, all inclusive. So if we don't have enough A's, then we can't make anything into A, which means that like we're screwed. So if the number of A's, CSI is less than CTI, CO, no. Another condition is that like we have to be able to reduce it to exactly CTI by using like by reducing it only by K. So therefore, like if I CSI minus CTI must be divisible by K. So if we reduce the number that we have to get to, then like CSI now contains the extra amount of A's that we have to get rid of. So if this number is not divisible by K, then like there's nothing we can do because we can only remove in groups of K. Not equals 0. Otherwise, it is, so we can do CSI plus 1 plus equals CTI, or CSI. And this works because this is like the only way we can this is the only way we can handle A. And then like next, we go to B. And if we don't have enough characters in B, we're done. Otherwise, we have to make it so we have exactly 0. And so therefore, we can't make anything into B. We can only get rid of B's now because we've already handled A. And so the only way to get rid of B's is subtracting them in groups of K. And therefore, we just check if we can do that, and we keep going. And then this is just saying we move all of these extra B's out to C. And then we also have to check if Z works, because we just do. Can print the letters in any case, yeah. Seems like it works. Do the counts, do them right, read in the strings. Then we just check. Okay. We have another game problem. Fun. That's a lot of pretests. Wow. Why are there so many? Huh. Because there are multitests still. Why would they need so many? Interesting. Alright, forced to play yet another one of Ush's games. I'm not going to try and pronounce names because last time I did that I was like totally wrong. So the game progresses turn by turn. As usual, he moves first. Consider the 2D plane. There's a token initially at 0, 0. One move, a player must increase either the x coordinate or the y coordinate of the token by exactly k. Exactly k. In doing so, the player that must ensure the token stays within a Euclidean distance d from 0, 0. Huh. Interesting. How would that work? Okay, this is a weird thing. So we have D and K. So essentially we have this like quarter circle. Or we have a Euclidean like what is it? Euclidean distance, we have Cartesian grid. And then we have this quarter circle that all the points must stay constrained to. And then we have this point here, and in one move, either we can move it up by k, or we can move it to the right by k. And essentially, we want to find the... So like each player can do this on their own, and essentially we're looking for the point where... like essentially who wins, who loses. And like you lose when you can't make a move. And you can't make a move if it'll take you out of the circle. That's how it works, right? Yeah. Okay, well this is like weird. So the problem is k can be small, and if k is small, then there's like a lot of possibilities for coordinates. Specifically, we have a circle with area, like big area. Let's go to Desmos. And we can plot this circle. So x squared plus y squared equals r squared. And we can set r however we want. So let's set r equals 5. We have like a lot of points. So with 5 and 2, say for example, we can move here, 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 and here. Then we would have 5 moves. We can move here, 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 and here. Then we would have 6 moves. Interesting. So each coordinate has like... Yeah, kind of like all of these are valid coordinates. So to be able to move 5 here, we can go, we have 6 over here, which is weird. Interesting. Okay, wait. Okay, so first of all, the game is symmetric, meaning that like if you move up, it's kind of this. Like if the first player moves up, it's the same as them moving to the right. So we can assume the first player will move up. Then like okay, so either the second player will also want to move up, and therefore the first player like let's say the second player moves up, and then the first player also moves up, and then they just like keep on going. Why am I using a different color? And they just keep on going until they hit the end. Say for example in the case of 5 and 1. I think I'm confusing myself. Yeah, okay. With 5 and 2 it should be there are like only 2 moves. But like in this case, the second player loses because now he's stuck outside the circle. So my idea is if the second player is going to lose if they keep going up, then they don't want to keep going up. At some point, they want to not do this and instead go to the right. Because if they keep going up, they will lose. So essentially, like, alright. I guess that's the idea. And in a similar manner, like if the first player will lose by continuing to go up, then it'll be the first player that wants to kind of break the chain. So for example, here. So now we're at this point, and now the second player has to decide where to go. Which is actually a good question. So if they go one way or another way, it'll like depend on what happens. Up to here, the moves are predetermined, but then I don't know. But this is kind of interesting, actually. It's almost like solving another subproblem. Like if we consider this, like this is, I'm not sure if it's its own semicircle, but it's like almost. Actually, no, it's not exactly its own semicircle. Like if these numbers were small, we can kind of brute force everything, but we can't, unfortunately. So it's not exactly a semicircle, it's something else. What exactly would we want to do? So I guess like, what would we want? Say going up will make the first player lose. And there's no reason for him to go up, maybe? Going up and make the first player lose, why would he ever want to go up? I'm not exactly sure. I'm not exactly sure of anything. This circle thing is weird. Maybe we can exploit the distance equation somehow. How do we even do that? So going from like x, y to x plus 1, y will increase the distance by like x plus 1 squared minus x squared, which is x squared plus 2x plus 1 minus x squared, which is 2x plus 1. Right. So every move will increase the total distance by 1, no matter what. But we'll also increase it by 2 times the current coordinate. which A proves that it's symmetric because x and y can be whatever. It can be swapped, it doesn't matter. And what else does it prove? Indeed, what else would it prove? What would this mean? I'm not sure if that means anything. If we consider it differently, like if the players let it go up to here, and then one of them is about to lose, so they stop, then what happens? Ugh, wouldn't love these types of problems where you guess the strategy and figure things out. Alright. How long is this round? Wait, what's the duration? This doesn't seem like... Seems like weird timing. Okay. This is exactly what I expected from this round, and I still am not happy with it. Actually, it wouldn't be x plus 1, I guess. It would be x plus k. So this would be 2kx plus k. Or rather, actually 2kx plus k squared. So if k is like not 1, then it's going to end pretty quickly. Okay, maybe there's some strategy here. Consider the middle of the circle. Like for example here. If they're gonna win in the middle, then someone can do anything they want to make it so they're in the middle. Would this work? Would the circle be too big at some point? Like let's say we let r equals 100. Would this work? Or would there not be an explicitly defined middle in a circle like this? So the middle would be square root. What would it be? Square root 2 over 2.707. So it'd be around 70. Around 70 here, around 70 here. So here the middle would be explicitly defined. Like say I'm going to win in the middle. Then whatever you do I can counter your move by doing the opposite, so that we always end up in the middle. Okay, the way I thought about this is by thinking like these circles, the number of moves it takes to end the game is kind of like a contiguous range. And so if we can get here, then we can also get here, and some player can always force it to be like here, for example. I feel like whatever the maximum number of moves to end the game is, the the player who's going to win can always force it to be that. That's my idea. I'm pretty sure that's true. Because like consider any coordinate x comma y. Then there also exists a coordinate y comma x on another point in the circle because it's symmetric. Then like say the first player goes here to try and circumvent it. Then the second player can move closer to the middle. Or actually, the second player can make it so they're like kind of at like this square from it. And then once you get to the point of being in a square, then you can kind of do whatever you want. Actually, I don't think that's true. You can't always achieve any coordinate, but you can always achieve the point in the middle because you automatically have this sort of square setup, I believe. I think that should be how it works, yeah. And then if you can always make it to the middle, which you can, then whoever's going to win in the middle will always make it so it ends in the middle, and therefore they'll win. And so the middle is the point where the number of moves is maximized because like it just is. And it is because I'm not actually sure how to justify it. But it's some sort of like area thing. It's the same principle that the thing that maximizes the area is a square. I guess. I'm not sure. There's some way to prove this though. I just don't know how to do it. D over k 1 equals 0. So essentially we're just gonna try all possible like ending points where we can't go any farther out, and then take the maximum. And then we'll use that to determine who wins. Max equals x. Now equals x, I is greater than or equal to 0, I minus minus, while d times x plus d times y plus 1 times y plus 1 is less than or equal to, what would this be? Oh, this would be k. The reason I'm doing this is because like essentially it's checking, like we're making y as big as possible for our fixed x. So like kind of as x goes down, y will sort of like monotonically go up. So plus y, max equals max x plus y. So if the number of moves is the most 1, then the second player wins, I guess. That'd be how that works, right? Maybe I have this like the entire thing flipped. Huh. What would this mean? Wait, so if there are 2 moves, who's first? Okay, so this is still wrong somehow, but which one's the wrong one? So 25 and 4. So there can be 6 moves. Therefore, he would win, or it would be Cn x plus y. Just gonna print like everything for comparison. Oh wait, actually it wouldn't work. We can only get to numbers that are like k, kind of. So actually we can start x from 0. Wait, how would this work? So x can be d over k. I equals x, I minus equal k. I think that's what we would have to do. So this doesn't even make sense. How would d times d be that big? Oh, it's because the number's big. Okay, sure. That's the last test case. Still doesn't work. Why not? So 125, 4. What was that? Right. 125, 4. And this is the problem. Oh wait, it should be I, not okay. It should be I, not X. Right. Because Y we fix, but I should be still wrong. Somehow. Why are there only like 2? Oh wait, no, it should be this. Because okay, yeah. This is the number of moves on the X direction that we make. Not the number of moves that, not like the distance we go. So it should be 8 now. Okay, there's some symmetry here. So this is the number of moves we make. And therefore it should be k times I. That k times I squared plus k times y plus 1 squared. While that's still possible, increase it. Then the number of moves is the current x plus the current y. And then we like print that. Okay. That sounds good. We don't mess anything up, right? This isn't going to overflow because this number is like already small in the beginning. And d squared is only like a small thing. Do we get a wrong answer? Who knows? Okay, looks like we're passing. Alright, how is that? Not terrible, not great. People have solved more things. Alright, but it's not terrible. Like, we're still making pretty good progress. How are other people doing? Actually, yeah, 46 is good. Never mind. What am I saying? Alright, close Desmos. It's an interactive problem. You have a hidden array A of n integers which you want to guess. Note that n is a power of 2. Okay. You're allowed to ask 3 different types of queries. You can ask for the bitwise and the bitwise or in the bitwise XOR. N is a power of 2. Each element takes a value in the range 0, m minus 1, and you can ask no more than n plus 2 queries. Oh, it's an array. Okay, not a matrix. Why did I think it's a matrix? Because I read this. I read matrix here, and that doesn't make sense. Wait, so n plus 1 versus n plus 2. What the hell? Interesting. Okay, so there's some strategy that works in the first one that just doesn't work in the second one. With like and the difference is a single query. That's actually pretty cool. Like, it's a single query that makes the difference between this whole thing. And a single query that makes the difference between 21 solves and 11 solves. Okay, but you want to guess the elements of the array. By the way, I'll try and prove this thing in D later, I just don't know how to do it right now. So I'll get back to that. I think the right size. Yeah. Okay. So you can get, right. What is this? Okay, say we knew the value of the first element. Then we can so we have this array that we don't know. Say we knew the value of the first element somehow. Then we can just ask for everything XOR that element and be done. That will take n-1 queries plus however long it takes to get the first element. Can we do that? Wait, the values are from 0 to n-1. Okay, so the values are also at most n. Is it a permutation? It is not. Can we get a value in 3 queries? If we can do that, we'll be done. That part seems hard. If we can do that easily, it wouldn't be an E, so we probably can't, but... Because that D was not easy for me, so this is probably harder. How do we even get a single element? What would be the strategy for even knowing a single element? Yeah, something interesting here. Say we had something like A1 XOR A2, and then we had A2 XOR A3, for example, and so on, like A3 XOR A4. Then we could actually get any pair of XORs, because like if we take the XOR of all three of these, we'll get A1 XOR A2 XOR A2 XOR A3 XOR A3 XOR A4. But like one property of XOR is that anything XORed with itself is 0. So these cancel. And these cancel. So we telescope kind of to have A1 and A4. Telescoping is like a math thing, or sort of everything cancels out except the thing you want. Or except like some sort of certain things. So if we had like, if we queried all of these, then we can get the XOR of like any two elements that we wanted. Question is, why would we want to do this? Also, I'm going to go to the bathroom and think about this for a bit. I'll be right back. Okay, I'm back. And something potentially of note that we can use with like any sort of bitwise thing is that each bit is kind of independent. In terms of AND, OR, and XOR, each bit kind of doesn't depend on the others. So we can essentially assume we're solving for an array of zeros and ones. So that's one way to think of it. Okay, now what I think we can do is let's do some stuff for the first two elements. So let's query their XOR. Okay, right? Now, if their XOR is 1, then we know that we have exactly 1 out of these two. 1. Otherwise, if their XOR is 0, then either they're the same, or then they're the same. So either we have 0 ones or 2 ones. So I'm going to note this in blue. So if the XOR is 0, either we have 0 ones or 2 ones. Now, how do we distinguish between 0 and 2? Let's take a different operation. Let's take their bitwise AND. And the reason that works is because, so now if the AND is equal to 1, then we know we have 2. And otherwise, we know we have 0. So now, like, if we have 0 or we have 2, then we automatically know these bits. We know this number. Because we just, like, do. Because we know either both of them are 0 or both of them are 1. So therefore, like, we know both of them. That's it. But the only problem is when we have exactly 1. So when we have exactly 1, we have to bring in a third element. Let's try and figure out what this bit is. So, let's see. Say we do bitwise AND. We know we have exactly 1, 1. So say we do a bitwise AND with both of these. Like, both of these are bitwise ANDed to this. So if either of these are, if both of these are 0, then, like, automatically we know this is a 0. Because we know at least one of these are 1, which means if this is a 1, then also at least one of these will be that. But otherwise, we know this is a 0. And so, if both are 0, then we know this is a 0. And otherwise, like if exactly one of them is a 1, then we know that this is a 1, and we can actually figure out which one of these is the 1, because, like, you know, we just know. Because if this is a 1, we know exactly one of these is a 1, and so we just know the bitwise AND of the 1 and the 1 is also going to be a 1. So if this is a 1, we actually immediately know all these numbers. But if this is a 0, then we know this is a 0. So we know this number. We know this number fully. We want to use this number to get this number. And so now what we can do is we know this is a 0, so we can take the bitwise XOR of these two. If this XOR is 0, then we know this is a 0, and we know this is a 1. And otherwise, if this XOR is 1, we know this is a 1 and this is a 0. So essentially, like, using 5 queries, we can find out the first 3 elements. Using 5 queries, we can find out the first 3 elements. Then the remaining n-3 elements we can find in 1 query each. So it's 5 plus n-3, which is n plus 2. So that should give us the first subtask. I think that would work. Now the problem is just to not screw this up. So cn to n. So first we query the bitwise XOR. So we find that bitwise XOR, the bitwise AND, the X2. Essentially, we're just like doing this all messily. So find the XOR of 1 and 2, find the AND of 1 and 2. I'm mixing the 0 indexing and the 1 indexing. Alright, first of all, let's find the power actually. While 2 to the k, we know it is a power of 2, so we can do that. Then this k is the number of bits in like the final answer. So we have AND 0, 1. Then we find the bitwise AND of the first and third elements. So this is 0, 2. Then we do the second and third element. So this is 1, 2. And this is the XOR of 0 and 2. Then this is A0, 2. Okay, now I'm going to set A0 size of A. Should be X0, 2. Right, now for each bit, first of all, a little V1, V equals XO1 and 2 to the I. So if V equals 0, V2 equals A01 and 2 to the I. So then if, like we so this is the case where we get this to be a 0, therefore we automatically know these values. So A0 plus equals V2, A1 plus equals V2. Then we can find out, okay, so the first case is these both are 0. Then we also have to find out this bit because we've already asked 5 queries. So we get the XOR of these two, which means we can just like do that. So if these are both 0 or both 1, then we can find this out with the XOR, which means that like V3 equals XO2. And this will be XORed with the Boolean form of V2. Actually, it should be like XO2 and 2 to the I. XORed with V2. That way, if V2 is 1, then we know that 1 is part of the XOR. So if this is 0, then their total XOR will be 1, which means that if we flip it, then we'll get this exact value. And this is only the case where this XOR is 0, meaning these two are the same. Okay, so yeah, first of all, we take the AND. If the AND is that, we do that. Then A2 plus equals V3. That should work ideally. And that will give us everything. Else, we know these are different. So V2 equals, let's see, A02 and 2 to the I. V3 equals A12. So again, if both of these are 0, then we know this value is a 0. If v2 equals 0 and v3 equals 0, then we know that A2 has a 0 here. We don't know about A1, so we have to do the XOR. V4 equals XO2 and 2 to the I. So the XOR will actually give us this exact value. All right, so if both of these are 0 again, then we check these elements and only those. Right, that's how this works, right? So XO2. This is a 0. So we know that this is the exact value. Yeah. So then like A2 plus equals V4. All right. A0 plus equals V4. A1 plus equals 2 to the I minus V4. That's essentially the bitwise not, but like a bit of magic thrown in, so we don't have to do some annoying operations. Okay, and otherwise we're left with this case where one of them is 1, and therefore we know the bitwise and is 1. But then just from that we automatically know the elements. So A2 plus equals 2 to the I. A0 plus equals V2. A1 plus equals V2. A2 plus equals 2 to the I. Because we know A2 is 1. We know A1 is whatever its bitwise and is, and we know A2 is whatever its bitwise and is. Because we have something here, and then we have these question marks. So these bitwise ands are only going to depend on this, like, 1. Right. So that's it, right? So either this initial XOR is 0, in which case we kind of, like, know everything already. Yeah. So then this is just the and then it depends on that and then this would depend on only the XOR. Then we use that. Otherwise, we know that we have exactly 1, 1 among the first two. So we check if both of the bitwise ands are 0, then we know this is 0, because otherwise it wouldn't be possible. We'd have to have at least 1, 1. And therefore, we can use the XOR to determine which one this is. If this is 0, then the other one is 1, and if that's 1, then the other one is 0. So that's exactly what we do. Oh, so this should be XOR 1 and 3. Right, so now we do that to the I minus V4. That's the opposite. And otherwise, we know we have at least 1, 1. So therefore, this is a 1. Because otherwise, it would be a 0 in this case. Then each of these is just their own value, because bitwise and with 1 is identity. And then the other is we know it's a 1. So now from here, we know everything. So now we just query everything else. Cout XOR 0 I plus 1 endo. And then we just straight up, wait, what is 2 to the 16th? Oh, it's like a big number. We XOR the 0 and I plus 1, and then AI equals C into X XOR A0. That we can just find out. What do we have to do? We have to print an exclamation. I assume that's the standard. Okay. No idea how to test this. So let's test it with this. So we have 0, 0, 1, 0. or 0, 0, 1, 1. Okay, so 4. We don't have test cases, right? We better not. Okay. 4. Alright, so the XOR of 1 and 2 is 0. AND of 1 and 2 is 0. The AND of 1 and 3 is 0. AND of 2 and 3 is 0. And XOR of 1 and 3 is 1. XOR of 0, this should be a 1. That's fine though, not a big deal. XOR of 1 and 4 is 1. Perfect. Let's try 1, 1, 0, 1. So it doesn't really matter what the last element is. 4. XOR of 1 and 2 is 0. AND of 1 and 2 is 1. AND of 1 and 3 is 0. 0, 1. And XOR of 1 and 4 is 0. 1, 1, 1. Yep. Let's try 2 different ones. The 2 being different are kind of equivalent to each other, so it's not that big a difference. So I'll try both of these. That should be exhaustive. 4. XOR of 1 and 2 is 1. AND of 1 and 2 is obviously 0. AND of 1 and 3 is... Actually, this is interesting. Yeah, okay, never mind. So AND of 1 and 3 is 0, 0. XOR of 1 and 3 is 1. And that's 0. 1 and a 1. Okay, one more, just to be sure. So XOR of 1 and 2 is 1, and is 0, and is 1, and is 0. XOR is 0, XOR is 0. Did I do something wrong? No, XOR is 1, and is 0. AND of 1 and 3 is 1, AND of 2 and 3 is 0. Oh, that is a problem. What happens there? I don't know. Wait, what? Good thing we tested. So we have 1, 1, 1, 1, which means it gets that one wrong. Somehow. And so that means it's A1. So if V2 is equal to 0 and V3 is equal to 0, which is not true. Oh, this should be V3. Whoops. This should be its own value. Right. Okay, let's try one more time. 4. XOR of 1 and 2. 1, 0, 1, 0, 0, 0. Perfect. Alright, let's try with the sample, which is 0, 0, 0, 2, 3, I believe. And we'll just do this simply. So A, 4, 0, 0, 0, 0, 2, 1 and 4 is 3. Perfect. So this will only work for the first subtest, again, because we take 5 queries to find the first 3 elements. Which is interesting. Looks like we're passing them. It's taking a while. Yeah, there would be a lot of pretests. Okay, so let's find... So this we have to reduce the queries by 1, and now I see how this problem works. So there are 2 strategies. There are 2 things we can do. Either we can totally reform the strategy, or we could just try and find it, so we try and make it so we can find the first 3 elements or so in fewer queries. Okay, that's not the best time, but it's working. Wow, we have the same rank? Seriously? We're still in 46 after solving this? Wow, that's kind of funny. How are other people doing? Get wrong answer on D. Yeah, I suppose you could. Okay. Right, now we gotta figure this one out. How do we do this? So, like, look at this mess of code. This whole thing is just to figure out the first three elements, and then everything else is so easy. But, okay. So what's the bottleneck of this casework? Well, the problem is if these XORs are zeros and ones, then that's the problem. So the idea is if we know this, if we know this bit already, then like we're good, right? So basically the decision tree is XOR equals 0. Then in that case we query the and then we're done. We know the first two. Then we just do a single other XOR to figure out the third element. Actually, yeah, then we do a single other XOR to figure out the third element. Also, another problem is that we're solving for all these simultaneously, which means that like the first few bits can be whatever. And so we have to be able to solve all of them in the same amount of queries, kind of. So otherwise the XOR equals 1. So actually we wouldn't need the bitwise AND in the case where the XOR is 1. Which is interesting. What would that tell us? Could we somehow save a query by not doing the bitwise AND? How would we do that? So like the thing is each thing independently will take at most 4 queries, but combined is the problem. Like fundamentally we're close. If we were solving for an array of zeros and ones, this strategy would work. The problem is we're not. And so that's the remainder of the problem. How do we sort of combine these strategies into something that will universally work? Also, how goes the room? I always like checking that. Okay, so we have multiple people who have solved E2, as expected. So we want to combine these queries. How did someone not solve B? Do they just move on? Huh. Okay. How would someone combine these queries? How would we, not someone, us, we have to do it. How do we combine these queries? So if the XOR is 0, then the bitwise AND is if the XOR is 0, then we know they're the same. Wait, do we even need the bitwise AND at all? If the XOR is 1, then we don't need the bitwise AND because we know it's going to be 0. So essentially it comes down to doing these 3 queries with the third element. But if the XOR is 0, we're going to do these queries with the third element anyway. So maybe we can deduce those values without doing this bitwise AND. Is that possible? So we have 0, I'm going to, actually wait, we have A0 XOR A1. We have A0 bitwise AND A2. We have A1 bitwise AND A2, and we have A, what is it, 0 XOR A2. This is kind of the same casework, actually. So this doesn't change. This whole part doesn't change because we don't need A01. The point is I want to get rid of this query. So how do we do this? I think it's the same casework as before, actually. We have A0 XOR A1. We have A0 A0 XOR A2, and we have A0 and A2. So actually, combining these two, by the same telescoping thing, we have A1 XOR A2 at the same time. And we also have A1 bitwise and A2, which means we can actually find the number of bits that are in the first and third elements. We can find the number. Is that enough? Does it tell us enough? So say we have problem is A1, I guess. What do we have for the, what did we do for the first? We did A0 XOR A1. We did A0 XOR A1. Okay, so first we find out from A02, or from this, we can figure out the number of bits set. This is weird. So we have this pair, and we have this pair. So using this pair, we can figure out the number of bits set in A0 and A2. Then using this pair, we can figure out the number of bits set in A1 and A2. And actually, we can do better than that. If either of these are fixed, like if either of these are automatically 0 or 2, then we can just find out the value of the other one using the values from the ones that we know. Otherwise, like, it's not. And therefore, both of these are 1. So we know we have 1 bit among these two, and we know we have 1 bit among these two. So the only possible cases are either we have 1, 1, and 0, or we have 0, 0, and 1. So we know A0 and A1 are the same. Man, we're so close, aren't we? How do we distinguish this in the first case? Well, this is where the bitwise AND comes in, actually. This is why we took the bitwise AND of this. Is there anything else we can find? I'm like frustratingly close here. Are either of these possible, actually? Wait. Oh yeah, this stems from the case where we know both of these are the same already. Okay. That's annoying. Is it possible to have enough information from this at all? Is there a slight reworking we can do? So again, XOR equals 1 goes unchanged. The only problem is XOR equals 0. And the queries we currently made are A01, A12, or A0 and 2, 1 and 2, 0 XOR 2, 0 XOR 1. So we can find X12 equals XO1, XOR, XO2. But then we can't differentiate this. And that's annoying because we're using XORs to figure out the rest. Like the array would be the exact opposite of itself otherwise. Maybe we have to use like some meta thing where we don't only solve bitwise. Actually, this is interesting. So we know no, it's still independent of each bit. That's annoying. No, we don't know. Never mind. It's not like it's the whole array that's constrained to this. It's only this level of bit. What I was thinking was we use like the information we have from here to figure out which case it is, but that wouldn't work. Because each level of bit is independent. There's got to be something we can do, right? So we know that the bitwise and we can find out the number of ones here and the number of ones here. Like if we could somehow figure out the total number of ones at the beginning, like the total number of ones of the first three, then we'd be done as well. But like the only information we have is information that is the same in both cases, which is so annoying. Unbelievably annoying. A0 XOR A1. Because again, this is it. If we can figure this out, we're done with the problem. And we need to rethink our queries. I haven't actually used OR at all. Maybe that's necessary. How would we use OR in a smart way? Could we bring in OR somewhere? Is my question. So the problem is the only relation we have between the first two elements is XOR. Meaning like that's just a problem because it means that no matter what we do, if they're the same, we can't tell the difference. Somehow we have to use OR. How do we use OR? So one OR, because if we could do with just AND and XOR, then like the subtask is just preference of whether you would rather use AND or. But like they aren't both necessary, and that's the thing. So maybe we have to combine them. The thing is, information in the first subtask is redundant in the second one. Or I mean these first two cases, making a query here is redundant in this one. But it's necessary for this one. What if we can find the bits in like a smarter way, maybe? If we did something like this or this. We could do something like this or this, or this or this, and this or this. And if these are all one, then the cases are like... And if we just like did some ORs? I'm just gonna try some random things. So if they're all one, then the cases are, so we have 1, 0, 0. So either this one can be 1, in which case we have anything. Or it could also be the case that we have this. Or we have exactly 1, 1. In which case it would be 0, 0, 1, or 0, 1, 0. Or we have no ones. In which case it's 0, 0, 0. So this case is predetermined. This case we find the value of this. And in this case we very almost find the value of this. Find a single value in 2 queries, or 2 values in 3 queries. We don't necessarily have to find everything. All we need to find is n values in n+1 queries. It doesn't matter that if we find the first, if we always find the first element, or if we always find the third element, it doesn't matter. But again, the problem is we have to do all possible cases at once. We could have a case where all of these 8 cases are in separate bits, and then we have to find all of them. So the hardest part is this one. What if we took like an XOR here and an AND here or something? So if we took an XOR here, we can distinguish between these cases and the rest of them. Sort of a wraparound. And we can take an AND here. Now that will solve everything. So it won't. Actually, it will. With 1, 1, we could tell which one is the one, actually. If we have 1, 1, we, like, know which one. Yeah, so this case is solved. Otherwise, we have all 1. So we take the XOR. In this case, we can solve this. But in this case, we can't. Because we can't distinguish this one and this one. We're at the same problem again. We try a different set of operations. Well, this case is still solved. But we can maybe take, say, purple means XOR and green means AND. So then we can distinguish this cases from these with the AND. But then with the XOR, it's not enough. With the XOR, we can distinguish these two. But now these two cases are the same. And that's the problem. There's always two cases. Okay, maybe we need to solve for 4 elements then. Because it's guaranteed that n is at least 4. How do we do it for 4 elements? Do we do 4 elements in 5 queries? That seems just harder in general. So wait. What if we did like 3 elements in 2 queries or something? It's like with these bitwise ORs, we have this many cases. It's a lot of cases. With 1 more query, can we figure out something else? I don't think we can. So we have 3 things to distinguish. What if we did 3 elements, and we do say an OR on one of them? Then we could do like an XOR on one of them. Right, then that leaves many cases. So this can be 1 and this can be 0 in any of these. We haven't figured out the 3rd element yet. But this will group together 1, 1, 0, 0, 0, 1, 1, 0, 1, 0. These are in no particular order. 0, 0, 1, 1. So now it groups these together. So therefore we split the problem in half. Oh, that's kind of interesting. Huh. We split the problem in half with one of them. Can we do it again now? Well, if we take, say, the bitwise OR of these, and now it doesn't distinguish much. So now I have like even more cases. Bitwise OR of these two. What will this do? Why will it be useful? Or we can do the bitwise AND in the same way. Well, if we took the XOR of these two, maybe, then it would give us the parity of the number of bits in total. So we have 0 bits, 1 bit, 2 bits, or 3 bits. And then these two would be together, and these two would be together. But we also know the number of bits in each pair. Actually, it wouldn't give us the parity of the number of bits in total. Because that would have to be the XOR of all three, and we don't have that. All we can get are pairwise XORs. What if we did 2 XORs like an AND and an OR somehow? Would that help us? 2 XORs and 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 OR. So here are the cases. This first XOR is 0. Then in this case, either we have this or this. So the first XOR we do is 0. Then either the first elements are 0, 0 or 1, 1. And otherwise, this first XOR is 1, so we have 0, 1, and 1, 0. Then we can use the second XOR. So the second XOR is 0. And we have 0, 0, 0, or 1, 1, 1. So all of them are the same. That's true, right? Yeah. Otherwise, if the second XOR is 1, then we have 0, 0, 1, or 1, 1, 0. Otherwise, if this XOR is 0, then we have 0, 1, 1, or 1, 1, 0. Huh, that's kind of interesting. What we can do is we can... Maybe that's all we have to do. We use AND and OR simultaneously. Does this tell us enough? This XOR is 1, we have 0, 1, 0, or 1, 0, 1. So no matter what, we have 2 cases that we have to distinguish. So if we take the bitwise OR of the first two, that will let us distinguish in these two. But it won't let us distinguish in the rest. How do we distinguish in these? Is it possible to? Is the case where the total number of bits is This is so annoying. If we do the bitwise and, then it's out of the same problem. Wait, this doesn't make sense. This would be 1, 0, 0. We always have to have 3 bits. This would be 1, 0, 0. Yeah. And like the fundamental problem with this is that these two are the same here. These two are the same here, and these two are the same here. And with the bitwise XOR, or with like the bitwise AND, for example, it only makes a difference when they're both the same. So somehow we have to cover all 3 of these at once. But like, can we? Is that even possible? Doesn't seem like it would be. And that is the problem. So what? So what can we do? We gotta do something. Can't just sit around being useless. We know these are complements of each other, so we just have to figure out which one is which. Glance at F, so I can see that I don't want to solve this and instead try and do E. It's a game, okay. It's a matrix. Choose starting cell, choose a finishing cell, decrease the value of the starting cell, pick any of the shortest paths. Either increase or decrease to leave the values of the cells unchanged. If the starting and ending cells are the same, then the value of the cell is decreased. Definitely not going to solve that one. Okay. Some sort of like nim variation or something? I'm not entirely sure. So it's down to E2. How do you do E2? It's like a lot of issues with this kind of counting. 568. Okay. There's a lot of issues with this. Alright, so maybe 3 elements is not possible. Or is it? If we like did some and here and some or here or something. And like somehow maybe we can combine the answers. Like say we did this, then we can figure out this one with the or. Then we can figure out this one with the and. We can figure out this one with either of them. And the problem would be this one. And, well, what else can we figure out with this? have an idea. It hinges off the fact that we can so if we query all the the XORs between elements, then we can get the XOR of any two elements however we want. So say we take the bitwise AND of these two. So then if these two bits are the same, then we know their value. This is like the same idea as the other solution. So if these two bits are the same, we know their value. And actually we're just straight up done from that. Otherwise we have exactly one more query. But I'm still not sure if this works. So we have two queries, and we have to figure out everything from that. Interesting that the values are most n. That says something. Actually, the values being at most n is important. I kind of forgot about that constraint. Because what that means is by pigeonhole, either you have two values that are the exact same, or you don't. Okay, wait. So by pigeonhole, if you have two values that are the exact same, then you're done. Yeah. Because then you can take their bitwise and find their values and be done. Okay, so that works. Otherwise, we have two values that aren't the same. Otherwise, every single thing is not the same. But I don't think it matters. Because again, we can do bits separately. Let's take two things that have XOR equal to 1. So we have AI XOR AJ. AJ is equal to 1. Then they're the same in all other bits, which means if we take their bitwise AND, we can find everything. Everything except for the one bit, which means we can use the strategy to solve for all the bits except for that one bit. And then we could take any two values that are the same parity. That is, their XOR mod 2 is 0, we can do the same thing. I think that works. Yeah, that should just work. Because by pigeonhole, stuff happens. Okay, so I'm gonna put this in a place where we can save it. And let's be smart. Alright. So I equals 0, I is less than n minus 1, I plus plus. Cout XOR I plus 1, I plus 2, and L. There's no way I'm solving F, so this is kind of my capacity right now, because F is some weird game thing. Then Cn to Bi. Okay, now for LLI equals 0, if Bi is equal to 0, and I'll just do this here, and so if Bi is equal to 0, that means the two adjacent elements are the same. or actually it means that A1 XOR A1, like the first element XOR that element is that, then cout and 1 I plus 2 endo. Right? Because that would mean that we have like 0, 0, 1. Yeah, it'd be that. Actually, yeah, this would be a 1 and I plus 2. Or no, this would be I plus 1 and I plus 2. Wait, okay, these are adjacent XORs. Maybe there's an easier way to do this. So we just did that like that. 1 and I plus 2. Then that would be simple. C into x. A0 is equal to x. C into A0. Set. So now for LJ equals 0. Set bit J 0 J and so this is actually a 1 XOR everything. Which means that to get something like 2 XOR 4, would this make sense? Feels like it doesn't make sense. Why don't we just like be normal? 2 XOR 4, you would have to subtract out the 3. Actually, wait, no, that would make everything easy. Would it? It would, right? So to get 2 XOR 4, it would be 1 XOR 2 XOR 1 XOR 4. Yeah. So now essentially like vector. So we know that 1 is not involved in a pair that's equal. And 4 I equals 0, I is less than minus 1. Plus vows that oh, this is weird. We need to find a pair that has the same XOR. If vowels bi dot size is greater than 0. Plus 1. Alright, it's the same thing. We're just checking for duplicates. So vowels bi dot push back bi. Because again, if these have the same value, then their XOR with 1 will be the same. Yeah. This makes sense, right? So just check if they're the same, then print 1 and I plus 2, because it's like indexing. It's I plus 1 plus 1. Starting from 1. Why don't we just do the exact index? That makes more sense. Not confuse myself. So then this is the same thing. Right, okay. Otherwise, we need something where it's like just straight up even. Yeah, it just needs to be even. Mod 2 is equal to 0. Print that. It's like kind of the same thing. Equals 1, I is less than n, I plus plus. Else bi. XOR 1. J equals 1. X, yeah, x and 2 to the j. be the same thing. 0, system1, A++. And this should be odd equals 1. This should be 1. That's not good. I haven't even defined this function. Cannot convert to long. Argument 1 to void set bit. What? Oh wait. 0. So I just need to stick this onto all of those. Zero, 0, 0, 0, 0, 0. What the hell? Guess I'm not even gonna compile. So let's go here. Oh, there's so many errors though. I'm so confused. 141. Like, what is this error? Yeah, this code is very screwed up. We're not gonna get this. I didn't even finish the loop. What the hell? Okay, yeah, no way. That's what happens when you try and rush things. I don't understand. There's no... What? Oh, I got rid of that. Yeah, my indexing is also off, so it doesn't matter. Just don't understand, what does it think is, I see. Yeah, well, did not get it in contest, but what can you do? I know my idea works, I just didn't like have it in time, which is annoying. I guess we'll try and implement this afterwards. Okay, so while system testing is going on, alright, I'll be right back again. We'll explain solutions afterwards. Alright, so without further ado, let us do solutions. I solved up to E2, I just didn't like get there. Let's see. I assume the rank is pretty bad. Could have been better. Yeah. Probably could have gotten like, let's see, where had I been with E2? Maybe like 5,500 points or so. Okay, so it would have still been pretty good. It's not bad then. Or it would be 400 points. That's how the decay works. So then we would have 5,400. Should be around here. Yeah, alright. So it just comes down to implementation speed, which I did not have. Alright. Don't have any idea for F, so I'll go over A to E2, and that'll be that. So the first problem, you have a number n. You can do two things. You can divide n by any of its proper divisors, proper being not n itself, otherwise it would be easy problem. Like you would just print 1. So you can divide n by any of its divisors that's not equal to itself, or you can subtract 1 from it. So you can reduce n to n minus 1 or divide it by one of its proper divisors. You want to find the minimum number of operations to make it 1. Now the basic idea is like, say n is even, then we could divide by n over 2, because n over 2 is a proper divisor of n, because n is even, and then we would get 2. And that would work. Because, like, n is just even. And then we would be done in a single another operation. But if n is odd, we can't do that. But what we can do is we can make n into m minus 1, so it's even, and then we can do that, and then we can make it 1. And so the idea here is this will take at most 3 operations. And so because 3 is a small number, like imagine any other divisor. If we make n into n over k, and therefore it becomes k, where k is necessarily greater than or equal to 3, then this is one operation. And then we need k minus 1 other operations to make it. We need k minus 1 other operations to make it 1. Actually, we may not need k minus 1 operations, but we may have to do some sort of thing to make it so it's 1. For example, we could divide by 2 again. But no matter what we do, making a number k that's greater than 3 into 1 is going to take at least 2 operations. Because you have to subtract at least once. You have to subtract either you subtract twice or divide once and subtract once or something, or divide once and subtract some number of times. But no matter what you do, it's going to take at least 2 operations, which means any other strategy will take at least 3 operations, and therefore this strategy will be optimal because it takes at most 3 operations. So essentially the strategy is to, if n is odd, make it even, make it 2, and then make it 1. And then you can check this in code just by seeing like at what point. Like the special case is if n is already 1 or n is already 2 or n is 3, for example. All these are covered in the sample, so you can just test everything. But yeah, you just check if all these moves are possible. That would be A. For B, you have a string. You have a binary string. That means it's 1s and 0s. And you have a bunch of queries on it. Each query gives you a range. And it asks, is there a subsequence that is a sequence of characters in order? Like it's just some subset of the characters of this string. Is there a subsequence that is the same as this when concatenated, but it's not contiguous? That means that there's like at least one gap between it where it's not the same. Like it could be the same everywhere else, but there has to be some gap between it. It asks, does there exist such a subsequence? And the key here is to focus on the ends. Consider this element. It has to be the first element. So what if we could like move this sort of out, and we can make the first element, instead of it being this one, it could be something in this range. Then it wouldn't be contiguous because we would change only that one, and therefore like this gap would exist, and it would still be the same because again we only change that one character and we change it to something that's already the same. The question is how we do such a thing, and well, that is the question, indeed. How we do such a thing? We ask, like, we just need to see if there's a 1 on this side, basically. And that's just it. Because if there's not a 1 on this side, then like that means this whole thing is 0. So no matter what you do, this 1 has to be here because it can't be anywhere before. And therefore it's not possible to move any other character in this string out to the left because the first character has to be at the same position. And otherwise it is possible because you can just get rid of this 1 and move it somewhere else. So if you have anything on the left that's equal to this character, then you're done. And otherwise, it's not possible to have it be something on the left. And then the same goes for the right. If you have something on the right that's equal to this character, then you're done. Otherwise, it's not possible to have it be on the right. So if there's no character either on the left or on the right that's equal to its corresponding character, then it's impossible, and otherwise it's possible, and that's it. That's the only thing you have to check. Again, because either you can move this over here, or there's nothing to move it to, so it just has to be like right there. That's the idea. So C is possibly easier than B. You're given two strings. Let's see, A, B, C, and B, C, D. And you can do two things. One, you can swap any two adjacent characters. And you can do all of these only to the first string. So you can swap any two adjacent characters, then you get A, B, and C, or A, C, and B. Or you can pick a group of K characters such that they're all together. Like, for example, say you had this, then you couldn't pick these two characters. They have to be together. But pick a group of K characters such that they're all together in a line, and they're all the same. And then you can change all of them to like the next character. So in the alphabet. So for example, AA would become BB, BB would become CC, etc. Just alphabet. So then, and what you want to do is you want to figure out, using these operations, is it possible to convert the first string into the second? And K, the group of the size of the group you have to pick, is fixed. Otherwise, it would be easy. Yeah. So basically, the idea is as follows. First, you can swap any two characters, which means at any point, and like you don't have to minimize the number of operations. So at any point, you can make it so you can have the characters be in whatever order you want. Which means if you have at least k A's, then using some sequence of swaps, you can make it so all the A's are together, and then you can restore them to their original positions. This is the argument of like bubble sort. Because you can sort an array with bubble sort by only doing adjacent swaps, you can get any ordering of the array in the same manner. So therefore, using only adjacent swaps, you can like make the array as ordered in any way you want. So then from here, it basically asks, so because we can order however we want, and we can order like the same to match with B, all we really care about now are the numbers of each characters. So we have some number of A's, some number of B's, some number of C's, etc. Dot, dot, dot. So we want to figure out, can we get the same number of A's in the first string as we have in the second string? Can we get the same number of B's in the first string as the second string? Same number of C's, etc. So let's consider what we can do. We can convert KA's into KB's. Or we can convert KB's into KC's, and etc. But notice that with this, we can't convert anything into A. Which means that, say we don't have enough A's. Let me continue this chain a bit. Say we don't have enough A's. Like, we have fewer A's in the first string than we do in the second string. Then no matter what, like, we're screwed. We can't make any more A's. So, like, there's nothing we can do. Otherwise, so like let A1 be the count of A's in the first string and A2 be the count of A's in the second string. Then like if A1 is less than A2, then the answer is no, it's impossible. Otherwise, we have that A1 is greater than or equal to A2. Now, the only thing we can do to make A1 equal to A2 is we can subtract K from A1 like some number of times, possibly 0. So what that means is that for us to be able to reach A2 from A1, A1 minus A2 must be divisible by k. So A1 minus A2 must be divisible by k, which means A1 minus A2 mod k is equal to 0. So if this is not true, then the answer is no. And otherwise, what you'll do is you'll move all of these A1 minus A2 extra characters. They all become B's, because that's the only thing you can make them into. So now we have more B's. And that's it. So now we move all of these extra A's into B. So now we have that A1 is exactly equal to A2. Right? So we don't care about A's anymore, because we can't do anything more with the A's. And so what that means is now we've solved for the A's and we're done with them. So now we have the exact same problem where we're starting with B's. We can't make anything into B's, and we do this exact same casework on the B's. And we do this exact same casework on the C's once we process all the B's. And we do this exact same casework on the D's, and etc. until we get to Z. And for Z, there's nothing we can convert it to, so either it has to be exactly equal or it's impossible. And I think actually it being equal for the first 25 also implies that it's equal for the last, but that doesn't matter. Like, you can just check it explicitly and be done. So that's the idea. And again, remember that you have to add these amounts to the next character because you're converting those. Yeah. Okay. So D, you're given a circle in a Cartesian plane. And in one move, you can either go right by k or go up by k, as long as you stay within this circle. The game ends when all possible moves would force you to leave the circle. So like the person whose move leaves the circle loses. So figure out who wins the game, basically. Assuming both players play optimally. That is, like, they've maximized their chances of winning. So first of all, it's zero, yeah, who's gonna win? And the basic idea that took me a long time to find is that, consider the center of the circle. If the person, say the game is predetermined, it's zero sum. There's some number of moves such that, for every sequence of moves, there is a winner. So notice that, the center kind of forms a square, which means no matter what moves you make to get to the center, it's going to be the exact same no matter what you do, provided that you do ultimately finish in the center. So what this means is that, the winner of the game, is obviously determined by the number of moves you make, because, specifically, it's the parity of the number of moves. If you make an even number of moves, and then the person who makes the next move is screwed, no matter what they do, they'll lose. Or say the person who loses is an even move, then it's the first player that wins, because they start with the odd moves. And if the person that loses, if the losing move is an odd move, then the second player wins. So it's basically the parity of the number of moves, which means that the person who's going to win at the center is predetermined, just based on the number of moves it takes to get there. So this is a square, which means that take some say let me redraw this now, get rid of all that. Say the first player is going to lose, so he makes some move, and the second player is going to win, so he wants it to end in the center. So the second player can just do the exact opposite move of the first. then no matter what the first player does, the second player will bring it closer to the center. And there's nothing the first player can do because the second player has control of their going to the center. And so it's like the same idea for the first player. If the first player will win in the center, then whatever the second player does, the first player can counteract it. And it's kind of like that same idea. And so actually it's not a perfect counteraction because the second player has like one move ahead. But the idea is, say this is going to, say the first player made this move. Then the second player has some move that like will let them kind of escape. I think it's just like not possible for that to happen. Like just based on how the circle will work. That's not about a fail system test, but like basically the idea is that every player can always bring it to the center. And if the second player has some tricky move, then like I think they just won't have this tricky move. Because the first player can kind of bring it up still. The first player should still be able to do that. Because they're winning in the center. So even though the first player can't perfectly bring it to the center, like they should be able to get close enough that it doesn't matter. Although again, I may have failed system tests. Who knows? But I believe that's true. So basically, the winning player is the one who's going to win in the center. And there actually could possibly be two centers depending on how the circle works. Oh yeah, actually, like, okay, so the position I was talking about is where the second, like, it would be the second player's move, and the next move they did would, like, bring them to the center or something. But, like, the way the circle works is that, like, there are fewer points away from the center than there are in the center. So, like, either the first player would still win because there are fewer points, or the second player, like, this point wouldn't exist, and so the second player would be forced to go into the center. That's kind of the idea. Okay, this is definitely not a formal proof, but it's sort of like the idea that no matter what, you can force it to be in the center. Right, and if there are two centers, then it's kind of just the same thing. Like, it's the same argument, it still works because there are two possibilities. And so it's even easier for the player who wins to win. And this is only possible if the two centers are symmetric, which means that, like, no matter what, whichever player wins will win in both of them. So now it remains to just find the center. And you don't actually have to do that. What you could instead do is just, like, pick some point. And then, like, say you're gonna shift x by k. Actually, what you do is you fix the number of x moves you make. So first you move 0 in terms of x, which means that, like, you want to go as high up as you can without breaking out of the circle. Because you're looking for, like, these boundary points. Because the center is going to be a boundary point on the circle. That is a point where you can't move anywhere else. So that means for each x, you just find the highest possible y such that it's still inside the circle. Like, for example, for 0, and then for x equals k, and then for x equals 2k, and then for x equals 3k, and so on. Then the center will just be one of these points. Because the center is, by definition, a point where you can't move up or left or up or right anymore. So for each value of x, you find the highest value of y, then, like, it's going to take x plus y moves to get to that point, so you can figure out the parity of that and figure out who wins. So you can figure out the highest y with math. I did some sort of two-pointers thing, because as the x, like, goes as the x goes up, the y will go down. With like you can just see it from the circle. So you can kind of maintain the y as you go along and just decrease it or increase it. However it works. And then the center is going to be the maximum. Okay. Yeah, so the center is going to be the maximum of this value of x plus y over all of them. And the reason the center is the maximum is because, like, it's kind of like the idea that if you consider some rectangle in the circle and you're trying to maximize its area, so for example, you have x and y, and you want to maximize xy constrained to like x squared plus y squared is equal to r squared, then the best thing you can do is to make x and y the same. Because if you have a big x, then x squared is going to be like even bigger. So y has to be small to kind of counteract that. But if x and y are the same, then like the effects of the square are as small as possible. Okay. Again, that's not a formal proof. You can use like calculus or something to prove that, but the basic idea is the way to maximize the area is to put it in the center. And so the reason that's like relevant is because like essentially with a rectangle that's not in the center, sort of like its perimeter is going to be smaller. And the number of moves it takes to move to a certain point is the perimeter of the rectangle. Actually, I guess you would want to maximize x plus y, but it's sort of the same argument, that you want x and y to be close together. So it's like the rectangle with maximum perimeter. And you can also optimize this in the same way and show that it is indeed true that you want x and y to be equal or very close. So therefore the center has the maximum value of x plus y. So if you compute all possible ones, then you can figure out the parity of moves in the center. Okay, that kind of is not great, but it works. There are also probably other ways to figure out what the center is. You can, for example, like just make moves like this until you get stuck. Like make diagonal moves and then try going up and try going this way if you can. And then that will also get you to the center. Like anything that works, basically, you just have to find this maximum, sort of. You have to find the number of moves it takes to get to the center. Then you can figure out the player who wins from that. Okay. How many times did I say center in the past 10 minutes? Jeez. Alright. For this problem, I'm going to go over both of them. Kind of. Like my weird and convoluted solution for E1. Actually, no, I'll just go over the E2 solution, and if you want, you can find my E1 solution in the screencast. Because the whole idea is you like find the first 3 elements using 5 queries in a really messy way, and then it just kind of works. Because once you have a single element, then you can query like every other element's XOR with that, and then you can figure out all the other elements from there. So that's the main idea. You want to figure out some element. Or at least some bit for each element. So the idea for E2, or my idea, is as follows. First, if you query A1 XOR everything else, say blue is XOR. If you query A1 XOR everything else, then like you can get the XOR of any pair easily. So you have A1 XOR AI and A1 XOR AJ. Then the XOR of both of those is A1 XOR A1, which is 0, because XORs cancel. XOR A1 XOR AJ, which just comes out to AI XOR AJ. So using m-1 queries, you can get the XOR of any 2 elements in the array. Now here's the idea. Say you have 2 equal elements, which means their XOR is 0. Then then you're done, because I don't know why they didn't just make the bounds small. That would be convenient, but if the XOR of any two elements is the same, then you're done. Because like that means you can take their bitwise and you just know both of them. Now. You can take their bitwise and you know both of them. And then from there, you can, like, say you know this one, then you can query this one XOR this one, and then XOR that XOR with this to cancel this element out, and then you're left with only this one. And you can do that for all elements and find out all the values. And you can, again, query the XOR of two elements by using this strategy. So then, yeah, now the strategy is to simply so that works if you have any two equal elements. And you can find two equal elements by like doing this sort of trick where like you can put all these values together and then sort them, and you can find a duplicate like that. It's basically just finding a duplicate value in the array. You can first explicitly check if anything's equal to A1, and if not, then you're finding a duplicate in this array, which is essentially the same as just like finding a duplicate in any array. And therefore you can do that normally. I did it in a weird way, that's why my implementation is so like ugly, but this whole code is just basically finding equal elements, or this whole code is finding equal elements. And then there's more to be done, though. If you don't have two equal elements, then like because there are only n possible elements, then like every element from 0 to n-1 must appear exactly once. Sort of like reverse pigeonhole principle or something. So therefore, there are two elements that have XOR 1, because n is at least 4. So consider some AI and some AJ, where AI XOR AJ is equal to 1. That means that, like, if you write them out in binary, all of their bits, except for the last one, are the same. All of their bits except for the last one are the same. Which means that you can use the strategy we just used at the beginning, find the XOR with this, and then do that, and then use that to determine all the other elements. You can use that for these bits. You can use it for every bit except for the last one. Which means that if you do the strategy for each bit independently, then now you know all of the bits of every number except for the last bit, the ones bit. But then then you just do the same thing. You find any pair of elements where their last bit, their ones bit, is equal. And then you don't care about the other bits, and then you use this strategy, again, to find the value of this bit for every single one. And the way to do that is to find any two elements that have even XOR, because that way that, like, the ones bit will be 0 in their XOR, so they're the same. So AI XOR AJ mod 2 is equal to 0. And then you use that to find the last bit, and then now you know all of the bits of all of the numbers, so you know the numbers. And again, because n is at least 4, it's kind of convenient in the sense that like you have at least 2 bits, so it works out. Otherwise, it would not be possible, I think. I don't think there's a solution for n equals 3, or n equals 2. And I kind of like went down the wrong path for a while, trying to extend my subtask 1 solution to subtask 2, but it just didn't work. So now the idea is to So that's basically it. The only ugly part is finding these pairs. And well, you can almost do the same strategy. Like, to find a pair where AI XOR AJ is equal to 1, it's the same as finding a pair where AI is equal to 1 XOR AJ. Or actually, it's more the same as AI XOR 1 is equal to AJ. But then, like, you can use these values. You can use the values of A1 XOR AI to do this. You can essentially, like, put AJ in like, say you go along. Say you've processed the first, like, k elements or something. Then what you can do is you can map each value of AJ to an index if it exists. So you can map each value of AJ to an index. And then when you're looking for AI, you can query the index of the value that has the XOR of this. So it's sort of like putting all the values with this value of A in some sort of vector or something, in some sort of list, or you can just map them to an index. And then you can ask this list of lists if there's a value for this XOR value. And if so, then you can find its index by doing that. And then you can use that to do the answer. And so the same thing kind of goes for the other one, where they're even. You can essentially just put all odd elements in one array, so for example I, and then all even elements in one array, all odd elements in another one. And then when you come across some element, like say you have x, and say you have odd x, then you ask the lookup table for any odd element. And when you find one, you're done, essentially. That's one way to implement this. It's ugly, kind of. What I did was very ugly. And in fact, it was like very not good. And I didn't finish it in time because it was so ugly. But that's the basic idea, that you can use this sort of lookup table approach. And yeah, that's kind of it. I will submit my E2, and you can see that in my submissions link, so you can kind of see how to do this. I just basically, like, this whole thing is the ugly lookup table thing, and it's not fun. Oh, and also for these two, you probably want to explicitly check, like, if A1 is equal to this, because the lookup table won't work if you have A1 as part of the pairs. So you would want to do that as well. Makes the implementation even more fun. Actually, I think it's not necessary, but I mean, whatever works, really. As long as something does work. You may actually be able to ignore that case, because such a pair, like these pairs should always exist in the last n-1 elements anyway. But like, yeah, essentially you can do this with a map or an array or however you want. You can map values to indices, then query certain points in the map. And here you would query the parity. And then you put AI in the map, and then you continue looking for future elements. And you put this parity in the map, and you continue looking if you don't find anything that's the same. So this is a fun problem, yeah. And again, if you want my solution that only works for E1, because it uses n+2 queries, you can find it early in the screencast. I'll have timestamps for everything. But that is the full idea. See how the rest of this goes. Okay, and yeah, this was around 685. So in terms of the future, there's some stuff going on like CodeChef. I'm pretty sure there's like contests like tomorrow or something, so that's going to be fun. Yeah, it is tomorrow at 11 a.m. for me. So I'll be doing that, and I'll do another screencast of that. So we'll get back to the Code Chef hype. In terms of everything else, that's basically all I got. So, hope you enjoyed. I don't have any idea what to do for F, so I'll leave it at that. It seems like some sort of nim variation. I don't know how to solve nim in the first place, or like, I'm not good at game theory. So, yeah, I don't know. Alright, goodbye.